afternoon, everybody. My name is Gavin Friend, and I am presenting on my soft robotic gripper project. I'm a senior student of the ocean engineering course. We're finalizing our projects for projects and design, and this is my presentation on what I've done these past 2 semesters. So we will begin today with a quick little overview of everything that's in the presentation. So I'll start off with the motivation, kind of why I did this. I go into a background of what is a soft robotic gripper. Go into the design process, so an overview portion of it, and then I go into the detailed portion of the design process. We then make our way down to how I manufactured my gripper and how I assembled the gripper. Then I go into some of the testing that I did and the results, and we break that down. I get into a conclusion, and then I kind of show the budget that I had for this project. And then I will be doing an in-person presentation today of how my soft robotic gripper works. Then we will follow it up with a quick little Q&A session. So to start off, we will be going through the motivation of why I chose what I chose. Currently in the research industry, there is a need for delicate and adaptable gripping in underwater environments. Typically, ROVs use these hard robotic gripper hands. They're made of plastic, metal, and driven by hydraulics, and typically they are a little bit harsh on the environment. So my goal was to create a gripper that didn't make this impact on the environments. So background, what is a soft robotic gripper? If you look in this image to the right, you see an example of one. This is just something, it's picking up some marine life under the water, and it's geared towards doing it gently, that way it doesn't actually harm the specimen. So, soft robotic gripper is a claw-like hand with fingers, which can be inflated rather than actuated using water or air. It's typically made out of a pliable material so that the fingers can bend when they're inflated. The material which is used must be able to stretch due to the fingers needing to have a minimum of 180-degree range of motion, and this will allow the hand to close. Soft robotic grippers are used to handle objects more delicately than a rigid robotic hand, and some of the applications include marine research. The medical field is currently using these, and the food industry does as well. So a little overview of the design process and what makes up a soft robotic gripper. So you must use a flexible material so that the top layer can stretch, such as silicone or TPU. Right here is your top layer. Must have an inelastic layer so that the hand can have access to bend around. This can be seen down here. This is a thick inelastic layer and a pretty thin inelastic layer. These can be created using various methods, such as pouring into a mold or 3D printing these fingers. And the design can either be smooth across the top, such as this finger right here, or it can have ridges such as this finger right here. All in all, the ridges make the finger stronger structurally and aid with bending, but no ridges are easier to fabricate. So kind of a detailed how I did my finger design and the process that I did to do it. My final design came from using an iteration method to nail down the final design. So I started with iteration 1, which was unridged, it had a thick inelastic layer, and as soon as I bent this finger, it cracked right down the sides. It was completely structurally broken and would not work for what I needed it to do. So I then went to iteration 2, where I had implemented these ridges, but they were very spaced out. I did a thinner inelastic layer so that it would bend a little bit easier, but it still did not completely go closed whenever I inflated it. So I had to go to my third iteration, which ended up being the final finger geometry. So as you can see here, my ridges are closer together, and this helps these little sections right here push against each other, which help the bending process because they kind of act against each other to make a closing motion. You can see a thin inelastic layer here. I also, instead of previously to get the air into these fingers, I had to drill a hole. This time I manufactured a hole already designed into the system. So whenever I 3D printed it, I just had a hole instead of having to drill one. So air could go in through here and go up through this channel like so. And then my final iteration also included a little set of ribs so that whenever the gripper has something, it's less likely to slip and it creates more friction. Finally, I created a little hub which would be able to hold the fingers, and I did this so that there were air channels which distributed evenly throughout the hub so that all the fingers would be inflated at the same time. And this here is a nozzle to where you can take a little spout and screw it in, and that will allow your air to travel into your hub. So for the manufacturing side of it, I modeled this entire system in Fusion 3D, sliced all of the parts using the Orca slicer, and then I printed the parts out of TPU using the Bamboo X1 carbon. When 3D printing, as you can see some of these lines here, you have minor little gaps which allow for air to seep out, which is what we don't need because we need our finger to hold its shape. So to combat this, I used a heat gun which actually melted the plastic after it was created, and then I sealed it with a silicone coating which helps further waterproof it and allow air or less air to escape. I also 3D printed my hub here. You can see the overall hub and then kind of like a little section view of it. You can see all of the little air channels which go right here, as well as all the little screw holes so that I can hold my fingers in place without having them fall out when we inflate them. This is the final printed product of the hub and the final printed product of the finger. You can see the little screw holes here where I can just put a screw down in there and it will hold them in place. For my system assembly, I used 4 fingers which were attached into the hub. I tapped a hole in the top of the hub to fit a 1/4 inch nozzle, and then a pneumatic hose was connected to the hub itself and then run to a brass T connector, where on one side you had a pressure gauge which gave me real-time data on my phone, and as well as created graphs for me about where the pressure was at what time period. And then you can see on the other side of the T connector that it goes to the air compressor, which was used to inflate the hand with air. If you look down here at the section view, you can kind of see how the fingers lock into the system. So you've got each of these go straight in here to their special cutouts. That air channel goes directly into the hand, and then from the top where this hose is, it goes directly in and then distributes evenly throughout the hand. For my testing process, I did 3 different forms of testing. The first test I did was a force test to see how much force each finger was giving off at different variations of PSI. So with this, I used a spring scale, which I looped my finger into, and as I inflated the finger, it curled around the loop of that scale and pulled against it to tell me how many grams of force were given off. You can see it follows a pneumatic hose here, it goes into the T connector. I was able to read the pressure real time with using my pressure gauge, and then this leads to the compressor, which was used to inflate the finger. Following this, a weight test was conducted where the hand picked up the same object at varying weight. So I had a bucket which I filled with sand, and I would fill it up a little bit heavier every single time. Then I would see at what pressure did the hand fall, and this was done using the real-time data from the pressure sensor. And then finally, wrapped it up with a coral test, which is actually the entire intention of this project. So put my hand on top of a piece of coral, I inflated it to see just how gentle it was on this coral, and this coral right here is very dry and very brittle. So my goal was to see if it harmed the coral in any way, shape, or form. And when it closed around the coral, there was no damage done, and I was able to fill it up to 50 PSI with no damage. And that is the entire basis of what I wanted my project to do. Going further, I'm going to further break down the test results. here's a graph. Right here you see the different weights versus what pressure they were at. And then on this axis you see the force versus the pressure that was given off. As you can see, these go up almost in a similar pattern. And this is due to, as this force increases, so does the weight that it picks up, because the force that was put on the hand actually goes into the object and creates a larger friction force, allowing it to pick up heavier things without it slipping out of the claw's grasps. So, as a little conclusion, I successfully designed, manufactured, and tested a soft robotic gripper. I was able to demonstrate flexible and controllable motion through pneumatic actuation. I gained different technical skills such as CAD design, additive manufacturing, and prototyping. Some of the soft skills that I learned from this are problem solving, because there was a new problem at every turn. I had a problem here, or this finger would bust, or this would break. So I had to kind of overcome those different problems. I also learned a little bit of time management, because while 2 semesters sounds like a long time, by the time you get to the end of it, you start noticing that you're running out of time very quick, and you've got to get a lot of tasks done before the semester runs out. So it kind of helped me learn how to manage my time effectively. That way I could stay on a steady rate of progress throughout this entire project and not get jammed up at the end. And then documentation. Prior to this, I've never documented the steps between whatever it was that I was building, but with this I had to. So it kind of helped me learn how to document each step and how I did what I did and why I did it. So that was an incredible help. Some of the future improvements that I believe could be made with this project are different enhanced sealing methods, because even though I was able to essentially blast the hand itself to melt the plastic together and weld it together, there's still a few small air gaps, so I would like to further enhance the sealing method. And then furtherly, I would like to actually integrate this into an ROV so that I can use it in the field, underwater, picking up different objects in the field. So those are kind of some of the future advancements that I would like to make with this project. Some of the different insights that I had for my project were starting off at what worked, the flexible design approach, using iterative CAD modeling and rapid prototyping allowed fast testing and improvement cycles. So I was constantly able to produce a product, see what went wrong with it, what went right with it, so that I could create a new example and further iterate my project where it eventually became a working hand. My material selection, I chose TPU because it provided the right balance between flexibility and durability for soft actuation. And this material has turned out fantastic. The only downfall is that when it's 3D printed, it's sometimes very difficult and can gum up the 3D printer, so you've got to be careful with it. Another part of my project which worked is a simple pneumatic system. There's a pretty straightforward inflation setup where you can use accessible fittings that you can pick up from Lowe's or Walmart or any other small stores like that, any hardware store pretty much. And this allows it so if something breaks in the field, you can go pick up a new one almost instantly. It's no problem, not gonna have a problem ordering parts or finding them. And the tubing that I use minimize the complexity of failures during testing, because it's just a pretty straightforward shot. There's no different couplings that can fall apart or let air out, so pretty much any air that got out of my system was through my hand itself. What could have been done differently? I would have liked to integrate different sensor testing, so having a force sensor inside of the hand as well as maybe a pressure sensor inside of there, so that I could get a full-on pressure and it be smaller, not have a big bulky pressure gauge on the side of it. This would allow me to get more quantitative feedback on the grasp strength and the object's interactions that it has. I would have liked to do some underwater field trials where I pretty much conducted a real submerged trial earlier rather than just sitting on the bench and testing it with dry objects in the air. I would like to be able to see how it handled the realistic scenario that it's going to be in. That way I could make design iterations to counteract that rather than just open air. And another thing that I would like to do differently is get a little bit of stakeholder feedback. So I would like to go out to a marine biologist or an ROV operator to see kind of, you know, what they've noticed is lacking in the robotic industry and what they would like to see, just so that I could implement some of these changes in there to help further improve my design so that it could be formed into a working project as well as a working business one day. So those are kind of some of the things that I wish I would have done a little differently. Breaking down my budget, you had my TPU filament, which was used to create 90% of my hand. We ended up ordering 2 rolls of it to kind of, because I went through a lot of iterations, different printing, testing this, testing that, and then eventually my final design. I ordered a PVA filament to actually print the supports out of originally, so that we could fill this full of water, and the supports which were used during 3D printing would actually melt out of the hand itself and not cause any problems. But I was able to counteract this with designing the supports in a way that I could actually not interfere with the different bending motions of the hand, and it would just be in there permanently. I had a silicone coating which was used to actually seal the project itself. There was a syringe, a very large one, that I used to connect to the hose before I put it to an air compressor, and I was able to pump this up so that it would eventually inflate. My digital pressure gauge. My pressure gauge gave me all of my data, all of my testing data, and it gave it real time, made it very easy for me, so it sent an Excel spreadsheet to my phone every time I completed the test, so I could see at what time it was at what pressure, so that I could compare this to any videos or any visual observations to see where it failed. I could see the exact point of pressure that it was at. You've got your spring scale here, which is used to test the force of my finger. It pretty much loops in there, pulls against it, and the different forces were measured in grams. And then your miscellaneous items such as my hose fittings and different nozzles and spouts and air compressor fittings that we ordered. That's kind of roped into that section, which gave me a total of $307.71. Next, I would like to complete a live demonstration picking up a piece of coal, which I don't have a piece of coal here. Okay.
There you go.
All right. Can you see me just fine?
We can see you just fine.
Alrighty. So we will begin slowly inflating the hand.
Do you need some extra hands from somebody?
No,
or
I'm
you
good. But I'll slowly inflate the hand until it makes contact, and then I'll inflate it a little bit more to ensure that there's the proper pressure, and it gives the force needed to pick up the object. You can see with very little pressure, it is slowly closing around the object. And then here at about 30 psi, it makes full contact with every single one of the points of contact, and I can now pick up the bucket. But as you can see, there's a little bit of slippage, so if I'll turn the pressure up a little bit more, it'll increase that force. Now there's no slippage, no falling, everything works just fine, no damage, and minimum bending to the plastic itself, so it's not going to cause any harm on a live specimen. Then you can just set it down, reduce the pressure going in, and then it'll open back up.
Very cool.
Any questions? Everybody.
So, where on the slide that you showed the slice images of the hub, can we go back to that?
Yeah.
So, in the center there, you can see that there's supports. How did you get those out?
I pretty much took a drill bit, put it on top, and hammered it down to kind of force those supports to be pushed out.
And the supports inside the actual finger, you don't think that they like caused any issues? Was that due to them also being TPU and being flexible?
I think when these supports are printed, they're printed pretty densely, so there's not very much stretching. But the way that this stretches, it bends around this way, and the actual sidewalls themselves don't expand out anymore, and that's the only part where they're connecting are the sidewalls. So everything is pushing from this wall, and
We can't
this,
see.
oh, sorry. So everything, all the forces pushing, these walls push against each other, but this side wall here never moves, it doesn't bow out or anything, so no, the only biggest issues I have were in these little cracks right here, and that's just because this was printed so small that there's just little air gaps that are hard to battle.
Have you ever tried printing without any support?
Yes, I did try printing without supports, but as it was filling in the top layer up here, it was pretty much just spitting filament directly into the hand so that my top layer wasn't as thick, which caused a bunch of different air holes and explosions to come out of those little spots. So I eventually had to put some supports in there, that way it had something to kind of run across at. I attempted to have it run to where it would run like this and have a smaller distance, but the slasher we were using, I was never able to figure out actually why or how I could use it to do that.
Thought about maybe instead of.
Speak up, Brody.
We thought about instead of having just a flat side, maybe like an arch side, so that the printing without supports could be lessened.
What do you mean?
So like an arch where the lower layers will support the upper layers as they're being printed.
I'm not sure. As if the entire finger itself was round?
Not if it was round, just on the inside. Currently it goes to like a 90 degree.
Yeah.
He's saying basically you had the inside of that would just have fillets.
Okay.
That way you have arches.
Yeah, the reason why I didn't do that is because the denser it is, the harder it is for the finger itself to stretch. So I was trying to minimize the amount of filament which was used on the internal cavities so that they would push against each other and flex around that degree of axis that I need with my inelastic layer. So while I don't want this to stretch at all, I want these different walls to be able to stretch completely.
This is more of a future question, but have you given any thought on how you would put this on a ROV?
Yeah, absolutely. I plan on putting a bracket on the back of this hub, or possibly just completely redesigning the hub with the same concept of air channels which go all the way throughout. But being able to mount that bracket to whatever hand of an ROV already exists, or even if we could take that hand off and just add this with a quick connect, I would like to design something like that. And then you could just put this entire project was meant to be used with water rather than air. So with us using water, we would just be able to use an inline water pump and just steadily pump that water into the hand itself. So you could just mount that on the back of the ROV and mount this on the front of the ROV, and theoretically, that's how I figured it would work.
If I put you into my time machine I have outside, and I sent you 10 years into the past where nobody has heard about 3D printing, what do you do?
In that case, I would take a silicone mold, and I would actually pour silicone into a mold, and then kind of put it together section by section, and only kind of glue those sections together. And that was something I actually thought about doing at the very beginning, but then I realized, some of the different parts weren't as structurally sound, and it was honestly pretty quick and painless, and this is a project that I wanted to be able to extend and further innovate. So I kind of got away from the mold pouring and went towards the 3D printing.
Yeah, 'cause you're quite lucky that they have 3D printers, right?
I
Your
am
project
quite
would have
lucky.
been,
That is for sure.
yeah.
And make do with the technology we have, right?
Oh yeah, no, it's good. Your project would be a pain just 10 years ago, so
Yeah.
it's great. You can take advantage of it. Yeah.
Any more questions?
Anything else?
Thanks
You good?
everybody for tuning in.
Don't forget to like, comment, subscribe.
Don't forget to like, comment, and subscribe.
That's right.